Looking again at the situation with the rail, the 0.4 Newton frictional force acts this way. The 0.4 Newton force has to be exerted by the rail to overcome friction. Friction's exerting a force on the rail has to exert a force back against friction. This force is exerted by and not on the rail. Okay, so these are not two forces acting on the rail. The only force acting on the rail is the 0.4 newtons. The only force pictured here that's acting on the rail is the 0.4 newtons, and that force is going to tend to slow the rail down. This is an important distinction that we need to be careful about. Okay, if we release the rail with 5.9 newtons of energy, if that potential energy in the rubber band is transferred, and most of it goes into the rail in the form of kinetic energy, then the question is, how far will the rail travel? Well, it's going to travel until the total work done by this force that it's exerting is equal to the energy that it has, the 5.9 Newton centimeters of kinetic energy. So that the force times the delta S is going to have to equal the 5.9 newtons. Of course, the force is 0.4 newtons, so we can easily solve for delta S. And what's going to end up is we're going to divide 5.9 Newton centimeters by 0.4 newtons, and that's going to give us just a little less than 15 centimeters. Then we can check to see whether that's consistent with how far the rail in fact traveled.